Hello everyone, Professor Dustin here, and this video is going to be an introduction to energy in oscillatory motion. So just like we just studied forces last class in oscillatory motion, now we can move on to studying energy. In some ways this is a little bit simpler than forces in the same way that energy is generally a simpler topic than forces, but we can get some more interesting information about these systems. So I've drawn a picture of a spring bouncing horizontally. I didn't put the floor in, but it's not moving in the vertical direction, it's only moving horizontally. I've put the equilibrium position to be x equals 0, so x naught is 0. And I've shown that it's going to bounce between some amplitude a in one direction and minus a in the other direction. So I'm sort of thinking of it going like, first it goes here, then it goes here, then it's maximized, then it's back to equilibrium, and so on and so forth, right? Maybe I pulled but maybe I pushed it in one direction some time ago or whatever, but it's now oscillating. So I want to study the energy of this system. So just remember the energy of the spring is stored as potential energy. So I'm going to write that as U to correspond with the way that I wrote things last semester. Spring, SP, and the formula there is 1/2 kx squared. So remember the k is the spring constant, which is unique for each spring, and the x is the displacement of the spring. And generally, you would have to do in there, you'd have to like delta x, like x minus x naught or something, but I've picked the center, the equilibrium point, to be x naught equals 0. So that means this is just either the extension of the spring or the compression of the spring. So that's the simple way of writing the spring energy. Cool, so if we want to figure out the energy in this system, we might want to do, okay, well, what is the total energy? Let's add up all the energy that's in this system. We might think about energy sources like gravity, like work due to non-conservative forces like friction, and so on and so forth. But actually, there's only two sources of energy here. It's the spring energy, which is storing the potential, and the kinetic energy of the block, which is just the block's motion, 1/2 mv squared. So I can immediately say the total energy of this system is easy to write down, 1/2 mv squared plus 1/2 kx squared. And of course, the v and the x are changing as the block bounces back and forth across its equilibrium position. Okay, so that's a pretty simple way of writing the energy due to the system. So let's just real quickly notice something that we can learn about that equation. We can pick our initial and final energies to be interesting things, and then try to figure out like, oh, what's happening as the system moves between its initial and final states. So let's pick the initial energy, the initial position of this thing to be like right here. So let's call that, when it is at its maximum negative position, let's call that initial. And let's write down what the energy is for that position. So that position has some kinetic energy and some potential energy. But of course, this is going to be 0 because the velocity is going to be 0 of the block, right? As the block bounces back and forth, when it reaches its maximum compression or its maximum elongation, the velocity momentarily becomes 0 before it turns around. So the velocity is 0 there, so that's 0 in the initial energy. We have just this, so I'm going to call that 1/2 kx initial squared. But I actually know what that value is. It's minus x, right? So the initial energy here is just going to be the energy at the point when the spring is at its maximum compression, which is when x is minus a. So and of course, minus a squared is just a positive a. So the initial energy here is just 1/2 k a squared. Okay, very cool. So now I've got the initial energy. We need to pick a state for the final energy. Actually, let me not pick a state for the final energy. Let's just write down generically what the final energy is going to be. And of course, what I'm going to do is I'm just going to write an F there, an F there, and F there. So let's just write that as EF is 1/2 kxf squared plus 1/2 mvf squared. Okay, so that's for some arbitrary values of x. And maybe I could pick this guy to be the final, and of course that's where the position is 0, so I could set that to be 0, whatever. But I want to leave it just general so that we could use this in other circumstances. So that's the initial, that's the final. Let's do our conservation of energy formula, which is that the change in energy is 0, which is EF minus EI is 0. Plug in that thing for the final, plug in that thing for the initial. Okay, But look at this expression. This is the maximum extension of the spring, right? That A. It's how far you pulled the spring this way or how far you pushed it that way. That's like a known value. When I set my spring up oscillating, I grab it and pull it and then let it go. So I kind of know how the magnitude of its oscillations. So now what this equation is, it's a relationship between where the spring is, where the block is, which is its final x position, and the speed of the spring. So let's think about this as a solving for what the velocity of the spring is, depending on the velocity of the block is, depending on what its position is. So from that perspective, I'm going to solve for v. So solving for v is going to be pretty easy because I've got, 1/2, kill the 1/2. Move everything to the other side that's not a v, so I'll have an mvf squared, and then a ka squared, and then a minus sign, because I move that over there, I get a plus sign, but move this over there, I get a minus sign, kxf squared. I can pull a k out, divide by m, take a square root to get the final answer. Vf is k over m, a squared minus xf squared, all square rooted. So that's the velocity right there. So what that tells me is, given my initial conditions, which, this initial condition seems like kind of specific, but it's true for no matter what. Like, no matter how the spring is bouncing, it's got some maximum extent. It's got some A at which it stops and turns around. So this equation is always true, even though it seems like I calculated it for a pretty specific case. As long as I know what A is, I can use this expression, right? But this says that if I just plug in the position of the spring, I can figure out what the velocity is at every single point. So these spring problems, because they're so similar to each other, you can kind of just do the same thing over and over. You can just kind of apply where the x position is and define the velocity using an equation like this. So that's the first note I wanted to make about these energy problems. Because the situation is pretty restrictive, we don't have a huge number of equations to deal with. We kind of just have things that look like this. Okay, so that's the first part of this video, is to talk about how the energy in the spring works. The second part is to sort of look at the graph of the spring and then talk about how the forces and the energies are related to each other in these situations. Okay, so I've erased everything except for our formula for the energy of a spring. First thing I want to do is plot that so that we get a sense of what that thing looks like. So a plot of this is going to be pretty simple. I'm not going to be super careful about the 1/2 k's and stuff. It's an x squared function. So that means it's a parabola. And if you remember from mathematics, positive x squared is the parabola opening upwards. So it's going to look something like this. Might not be the world's best parabola, but fine, it's a parabola. Now, something we learned last semester when we studied graphs of potential energy functions is if we have a graph of the potential energy function, we can actually learn quite a lot about it. So, for instance, if you know what the energy is of the system, so let's assume that we know the energy is whatever, E naught, some energy level. If you draw in that energy level, where that energy level intersects the potential, sorry, I should have drawn and said that this is the potential as a function of x. It's this equation. So where the energy level intersects the potential, those are the turning points. That's where the object stops and goes back the other direction, and then when it hits the other side, it stops and goes back the other direction. So that's from Physics 1, but actually now this is what the spring energy looks like. We know what those positions are as x positions. That's A and minus A. That's the amplitude of the motion. So as the object starts at the center and goes towards more and more positive x, when the energy level is the same as the potential, the kinetic energy is 0. That's its maximum extension of the spring. And when it goes back the other way, that's the maximum compression of the spring. It gets minus A from the equilibrium. So cool. So now we have some values associated with what we did last semester, talking about the graphs of potential energy functions and the turnaround points. Very nice. So now let's try to understand how this system looks when we talk about not just the energy of it, but the force of it. So there is the force associated with this energy of interaction. So there's a formula that relates potential energy and forces, which I wrote down last semester. We didn't do a lot with, but let's look at it. So it turns out that the force for any conservative interaction, and the spring is a conservative interaction, is the minus of the derivative of potential with respect to x. So this derivative, that's a slope, remember, but it is just a derivative. You could just calculate it as a derivative, but the derivative is also the slope. So let's try to make sure that we understand how this works associated with this energy. So the slope here at the center is 0 because it's flat. The slope gets more and more positive as we go this way, meaning that the slope of the function gets larger and larger as it goes more and more positive. But this way, the slope starts 0, and the slope is negative and gets more and more negative as you go. So what that tells us is that the force has a negative sign associated with the slope, so that means that the force gets more and more negative as you go towards the positive direction, and gets more and more positive as you go towards the negative direction. So that means that as you go this way, the force is getting bigger and pushing it that way. And as you go this way, the force is getting bigger and pushing it that way. And of course, that's what we expect from a oscillatory motion on a spring, right? As the spring gets extended, it pulls harder and harder and harder until it pulls so hard that it goes backwards. And then as it goes the other way, it pulls harder and harder and harder until it goes backwards, right? So that seems consistent with our understanding of springs. Let's also just plug in this equation into the U there to make sure we get something out of the force that we actually understand. So I'm going to calculate minus d by dx of that 1/2 kx squared. So that's pretty easy. The 1/2, the minus sign was from the formula for the force. The 1/2 comes out because it's not dependent on x. The k comes out because it's not dependent on x. X squared, that's a 2. 2 drops down to 1. 2 gets pulled out, cancels with the 1/2, and we get the final answer there of minus kx. 2 canceled k. Yeah, great, which is the formula for the force that we studied just last class. So great. So this seems totally consistent with the force of the spring, and I'm actually going to put the spring in there. Because now instead of just talking about a generic force, I'm actually talking about the spring force specifically. So we got that. And we now understand what this means. As x gets bigger, the force gets bigger positive, the force gets bigger in the negative direction. And as the x goes negative in this direction, the force gets bigger and bigger in the positive direction. Cool. So this physical situation has a very special name, and it's called a stable equilibrium. So equilibrium, because there's a point right there where I can put something and it won't move. So that's called equilibrium. Let's switch colors. Equilibrium. I can put an object right there and it will not move. This whole system is called a stable equilibrium. That point is a stable equilibrium because if I push it away, meaning if I displace the point a little bit, it goes back to the center, crosses the center, goes the other way, but then because of the force and energy interaction here, it then goes back towards the center and on across to the other side, and it goes back in the negative direction, and it goes back in the positive direction, and it bounces back and forth in an oscillatory fashion. So that's a stable equilibrium. Stable because it keeps going back and forth forever and ever and ever. If I just set this thing oscillating, it's going to oscillate until the end of time because I didn't put any friction on it or anything. That's called a stable equilibrium. Now, just to contrast, let's do a real quick example where we actually have an unstable equilibrium so you can see what the difference is. Okay, so there's some kind of weird potential. It's, on the right-hand side, it's the same as the spring potential, but it's kind of the opposite of the spring potential on the left-hand side. It doesn't really matter what this potential is. I'm gonna, if I wrote down the formula for it, it would be something like, kx to the third. Because the concave up situation is a parabola. This non-concave situation, it has to be a third order polynomial. So it's something like that, but it doesn't really matter what it is, right? It looks like that. Okay, so let's study this system in a similar way we studied this system. The first thing to notice is because the slope of the potential is the force, there is a 0 in the slope of the potential, and that's right there. So right there, maybe my picture is not super great, but I did try to make the slope kind of 0, right? So the slope right at x equals 0 is supposed to be kind of 0, right? So that means the force is 0. So if I drop an object right there, it will stay there because it doesn't have any force on it. So there's actually an equilibrium in this situation. It looks a little bit weird because it doesn't have the same equilibrium as this does, but the slope is 0, so it definitely has an equilibrium point where there's no force. However, if we do this moving back and forth in the diagram, we actually notice that something very different happens. What happens here, if I send the object this way, go up the slope kind of, then the same thing happens as it does over here. It goes up the slope as far as the energy that I gave it. Let's say it goes up to here, and then it stops, and then it goes back. So it has the same behavior on the right-hand side. Also, if I drop the object there, it would go this way, right? It would go towards the left. But, and it has the same force relationship, has this negative slope, so positive slope has a more and more negative force, so as it goes this way, the force gets bigger and bigger, but in the opposite direction. Now, on this side, something quite different happens. As the object crosses into the negative x region of the graph, the slope of the potential is actually still positive, right? This is a positive slope the whole way. In fact, it's getting more and more positive as it goes down, right? So the slope is not changing in sign as it changed over there. So if the slope is positive here, that means the force is negative, so the force is going that way. But here the slope is still positive, and actually it's getting more and more positive as you get more and more negative in the direction. So the force is getting more and more negative. So in fact, the force doesn't respond by switching direction; it just stays negative. So you can say over here we have a force which is negative because it's going that way, and here we have a force which is positive, greater than 0. Here we have a force which is negative, going that way, but over here we still have a force which is negative. So that means that although this is an equilibrium point, if I push the object this way a little bit, once it turns around, it's never coming back, right? Once it goes up here, the force stays negative when it crosses the equilibrium and it just flies away. So this is actually called an unstable equilibrium. Unstable. Instead of stable equilibrium, which was here. And they're characterized by what happens to the force on either side of the equilibrium point. So over here, we have, on this side we have a stable equilibrium because the thing will bounce back and forth forever. That's what stability means. That's a bouncing spring back and forth. Unstable means that I push it a little bit in one direction and just zoom, goes the other way. In fact, if I push it this way, it will just zoom, go that way. An example of an unstable equilibrium would be like balancing a marker on your hand, right? Like you can do it, but as soon as you touch it a little bit, it's gonna fall, right? So you can like try to make it stay, but eventually it's just gonna fall off. The typical example we also talk about is trying to balance a pencil on its point, right? Technically, you can do that. Technically, you can get that pencil balanced exactly, but as soon as you touch it, it's gonna fall. So that's the kind of equilibrium positions we talk about when we talk about unstable equilibrium. Springs are stable equilibriums because they bounce back and forth forever. Okay, cool. So those are the two major topics we're going to talk about in class, are the energy sort of associated with the oscillatory motion, which means we can sort of do two different things. We can describe the position and the velocities of these objects pretty easily just using the energy equation, and we can also do these kinds of discussions where we can just plot out the energy and look at where the equilibria positions are and decide something about the motion just by looking at those equilibria positions. Okay, cool. Hope this has been helpful and clear. Thanks very much for watching, and I will see you in class.